That finally gives me the discrete Fourier transform. Or DFT for short. So note that in the equations before, when I already mentioned Fourier transforms, I didn't have this factor here. And there are actually different conventions. So there's a Fourier transform, and there's the inverse Fourier transform, and you can either have the constants only in the forward transform, or only in the backward transform, or you can partition them and have them in both. Which means the most writing work, because no matter if you transform forward or backward, you always have to carry these normalizing constants. But on the other hand, it makes for the most symmetric representation and gives you a unitary transform. So that's why I'm using this convention here. And secondly, note that there is a complex conjugation there, because the Fourier basis function is e to the plus I, etc., etc. And here we have an e to the minus I, etc., etc. This is why I need this complex conjugation. So this was just for the kth eigenvalue, and if I want to do it for all simultaneously, I can write that first writing it as a row vector, so G transform transpose. And here again, I need to take the complex conjugate of my matrix of basis functions. But now I want a column vector instead. So I want G. And that is F complex conjugate and transposed, which is the adjoint of F, times G. Which is also, can also be written like this. So this would be a matrix notation, and this would be operator notation. And you see that our operator is just a matrix. Sometimes this is written in a different way, namely in terms of a matrix W times G, just to get rid of these extra symbols. Yeah? So we have the normalizing factor here and the complex conjugation and transpose. And to hide these, we can define a matrix W, where W is small w to the power of j and k divided by the square root of n. And this would be element jk of this matrix. and this complex number is an nth root of unity. It's completely equivalent, just a different way of writing the same thing. I will mostly use this notation later on. And for completeness, let me also write the inverse transform. So G is 1 over square root of n f G transform. And if I insert the result from above, you see that this gives me 1 over n f adjoint G. Oh, and I have a problem. Something's wrong here with my... yeah, it's fine. This here is n times the identity matrix. Or in other words, if you want it component-wise, the nth element of G is given by the following. This time it's the frequency that runs from k from 0 up to n minus 1. This time we have a plus I 2 pi over n kl. So this is the inverse discrete Fourier transform. A word about the cost. If I did implement Fourier transform in this way by matrix multiplication, I would find that it's O of n squared, because this is what I pay for the matrix multiplication. But the cost of the fast Fourier transform is only of order n log n. I have some pretty pictures here. The first one is from the book of Bernd Jerne, who is working in this institute here. And I'm showing here 3 pictures that illustrate the same thing over and over. Okay, and because it's important, I will go through each of these. So the first picture shows me just half of my basis of Fourier transforms. So I've marked this in yellow. 0 is the lowest frequency. And actually, if we have signals of length 16, then 8 is the highest frequency, beyond which the frequencies start to decrease again. So with the Fourier transform, I'm getting this pattern. So let's say, as in physics or so, we're used to the following. Let's say we have some stochastic process with a spectral density, and let's say there's more energy in the low frequencies. I'm drawing this now in the continuous domain here. And then by periodicity, we have the same spectral density appearing here and appearing there. So this is how us humans, we think of it, and we think that this is the spectral range. But now note that our convention, now this here is frequency space, K. Our convention is that we consider the values from 0 up to n minus 1, which lies just to the left of the center here. So in other words, we have the low frequencies first, and then the high frequencies, and then again the low frequencies in our basis functions. And that's what you don't see in this plot. So we have, well, the constant is the lowest frequency you can imagine. Then we have 1 oscillation, 2 oscillations, 3 oscillations, and so on, up to 8. But this is only the first 8 out of 16 basis functions. So the next ones will actually have the same real part as those above, but the imaginary part, which is shown on the right, will be conjugated. And by the way, here you also see that the first element, the DC, so this is the DC term for direct current as opposed to alternating current. So Gleichstrom versus Wechselstrom in German. The DC term here, the basis function, is purely real. See, its imaginary part is strictly 0 and its real part is 1 or constant. And the same holds for this basis function here. So these two Fourier coefficients will always be purely real, whereas the other can be imaginary. Now here is for a signal of length 10, another representation. We have the complex plane, and I have here plotted the position of the complex plane in terms of the HSV color space, which you know now, and our complex plane wave, we said, is a spiral, or is a, we're walking along a circle in this complex plane. And this is what you also see here. This is the matrix F, where the elements or the complex elements are color coded. So the first column is all constant. This is every entry has the value 1 over square root of n. The next entry corresponds to 1 revolution in this complex plane. And you see that the direction, you see by the colors that the direction was as I had indicated. So this tells me I'm looking at F and not F star. Then this one here, this column already has 2 revolutions. So I go around twice until I reach here, and then we have 3 revolutions and so on. And then we find eventually the highest frequencies that we have in the signal before going back to lower frequencies. So you see this one, this column here is practically the same as this one. It's just that they're flipped upside down, with the exceptions of the first term. What I've shown on the left-hand side is the basis of single pixels or of single impulses. So whereas this is the Fourier basis. What I wanted to stress here was if we have a basis of impulses, we are perfectly localized in space. So each contribution tells us exactly how much of the signal is at a given point in space. Whereas in terms of the Fourier basis, each of these basis functions is completely delocalized over space. But this is an orthogonal, the left one is an orthogonal basis and the right one is an orthogonal basis. And in other words, we just, when we present our signal or our image in such a different basis, We just rotate it into this different basis. So our unitary transform is just a rotation, but into a basis that has a very different character. Finally, here's another picture from Wiki for a signal of length 8. And, well, what you see here in the first half would be another representation of what you saw in the picture from the Jene book. So if we look again at the formula here, where we say that we take this matrix product, or this product of a matrix and a vector, we can think of this as a matched filtering process. So F adjoint G amounts to a matched filtering. It is a cross correlation of our input signal with the number of pure frequency complex oscillations. So in a way, the Fourier transform tells us how much of a complex oscillation of a given frequency is in our signal and at what phase shift. So in other words, we decompose any signal or any image into a basis of complex oscillations or plane waves. This may be somewhat intuitive for, let's say, audio signals, where in our intellectual tradition we have for a long time written musical scores to say, you know, here's a deep tone or here's a high tone, but we find it quite counterintuitive for images to represent an image really in terms of regular undulations. And yet this is what the two-dimensional Fourier transform does. Do you have questions? The fast Fourier transform, it exploits the structure in the matrix. So as you saw in, for example, in this representation here, the matrix has a special structure. It is composed of a single element which is taken to various powers. And that means we do not really need to take the full matrix multiplication, but we can reuse computations. And the FFT does that by essentially first taking Fourier it first considers the signal as duplet, so as many signals of just length 2. And it computes a Fourier transform for each of these, which is very simple. And then it aggregates the signals and operates also on the coefficients at the same time. So I didn't want to talk about the algorithm here in detail, but it's one of the algorithms in the book. Capital. Oh, this is the thing, you know, if God had a book of algorithms, this would be in it. Yeah. Oh, why do we need the Fourier transform in general? Oh, would he need to Fourier transform? Yes. Well, I assume he has this library for his pleasure. Not a theological authority here. All right. I want to start by correction and then mention important properties. The correction is that I said that, for example, for a signal of this length, this term and that term, oh, sorry. I said that this term here and that term there, they would always be real because the basis functions are purely real. That is, of course, only true if the signal also is purely real. So when the signal is complex, then these coefficients can also be complex. Okay. So there are loads of important properties. I will start by a bit of terminology. I've said several times that any LTI operator can be characterized, can be fully characterized in terms of its eigenvalues. And these eigenvalues then, of course, have a special name. They are called the transfer function. So altogether, they are called the transfer function. This is the symbol that I used, and there's another symbol saying this is the Fourier transform of that, and that was called the impulse response. So the first live in space and the other live in reciprocal space. So they live in space or time, and they live in reciprocal space, or sometimes this is called k-space, and it has other names. In image processing in particular, you know what the impulse response is called? It's the point spread function when we talk about optical imaging. So let's say we have an ideal point source of light, but in practice, due to atmospheric distortions and more importantly, what's going on in your lens and so on, you will see not a single point, but something that's slightly blurred, and that is described by the point spread function, which is the same as impulse response, it's just the term used in imaging. And accordingly, that is then called the optical transfer function. And this transfer function allows us to read off very conveniently what an operator is doing. So, for example, this one would be an operator which lets the low frequencies through and attenuates the high frequencies. So this would be a low-pass filter. That, in contrast, would be a high-pass filter, or we could have a band-pass filter and so on. And to create filters which look as desired in Fourier space but are as compact as possible in the spatial domain, that is a typical optimization problem. Next, I want to look at the symmetries. When you implement these things yourself, it's always important to distinguish if you have an even or an odd length of your signal. I'm helping myself with tiny pictures like these. So for n even, this would be k, 0, 1, 2, 3. So for 0, this is the DC term, about which I will say a little more. This is the highest frequency that we can observe, and these here represent the same frequency. For n odd, picture is a little bit different. So here the highest frequency would be somewhere in the middle. Now, in particular, we often have signals. We measure often signals that have only a real component, and it is possible to show, I'm not doing it here, that if, for example, G is purely real, then its transform is Hermitian, meaning that the transform evaluated at frequency minus k is the same as the complex conjugate of the transform at frequency k. And if G is even, where now by even I mean symmetric around the origin, maybe I should say symmetric better. So GL equals G minus L. Then its transform is also symmetric. And if you remember these two, then you can infer most other properties. I want to show one particular example. If G is real and symmetric, have the following. I'm writing the Fourier transform, but decomposing it now into its real and imaginary part. And if GL is, or if G is symmetric around the origin, so this thing is symmetric and this thing is anti-symmetric, then the entire expression cancels. And on the other side, I find that this is symmetric and that is also symmetric, and hence the overall transform is real and symmetric. Yeah? Does what need to be different? Sorry? No. Does one of the G's need to be different? No. It's no, I can write the Fourier transform in its common shape, and I've now rewritten the complex exponential as a cosine minus I times the sine. Okay, so bottom line, if my input signal G is real and symmetric, then its transform is also real and symmetric. And this is something which is exploited in the discrete cosine transform that we'll talk about more next week. Okay. Then I wanted to mention particularly the DC term. The DC term is the name of the Fourier coefficient at frequency 0. Frequency 0 means this entire thing is always 1, and we hence have a summation over our entire signal. So the DC term, or the Fourier transform at frequency 0, the Fourier component at frequency 0, gives the sum of the signal. And this can be useful in thinking about operators. So for example, if I want to know what the derivative operator in K space will look like, you know that if I take the derivative of a function that is the same regardless of whether I add a constant to this function. And that tells me already that the derivative operator must have a DC term of 0 because it annihilates all such constants. So I don't know yet what the derivative operator looks like for the other frequencies, but it must definitely be 0 at 0 frequency. And we'll revisit the derivative operator soon. Okay. Then the shift theorem, or the modulation theorem. So if I'm looking at the Fourier transform of a signal G which has been shifted by an amount of L, I use no longer here the index J, but J minus L. And I can then substitute some variables. So I'm creating a variable U, which is given by G minus L. Okay, now I'm inserting that this J here is given by U plus L. So I'm using the U here, multiplying the whole thing with that. First part is again the Fourier transform. My summation here does not go from 0 up to n minus 1, but since it's periodic, it does not matter where I start and end with my summation. Okay, so it's okay to start here at minus L and go up to n minus 1 minus L. So this is G transform at frequency k times e to the minus I 2 pi over n KL. And there was a K missing here. So what we had originally was our shift of our signal, and that amounts to a modulation. So multiplication with an oscillation amounts to a modulation of its transform. The practical application of this is to estimate shifts in the frequency domain rather than cross-correlate two signals to find the proper or the best shift that superimposes the signals. You can Fourier transform both, divide them, and look at the resulting signal and estimate from this modulation signal, which can be noisy, its frequency. And that will give you the amount of shift. Now, probably the most important theorem of them all which is the convolution theorem. To find the optimum shift, let's say we have some signal G and we have some signal S times G where a shift of L had been introduced. Yeah, we're trying to find L. I can compute the transform of G. I can compute that which, if the signals are really perfectly identical, will be the same with this modulation here. I'm adding the indices here to get just a number, not the full vector. And then I divide one by the other. Yeah, so now I divide this by that. The transpose cancels, and I'm left with just the modulation term. I do that for each frequency, and I hence get out if everything. So if the two signals were really perfectly identical, I would get out a pure modulation as we've seen before. So this is meant to be a perfect spiral. In practice, if there's noise, I will get something that looks a little shaky. But you can still try and estimate the dominant frequency of this. So I can now get the spectrum. The spectrum of this would be a pure peak somewhere because it's a pure frequency. The spectrum of this will be something a little broader, but still allowing me to estimate the location of the maximum. And that would be an estimate of the frequency of this thing, which translates back to the shift between the signals. So you're mentioning the convolution theorem, which we will talk about in a minute. And the convolution theorem indeed tells us that in the spatial domain, this multiplication in the Fourier domain corresponds to a convolution in the spatial domain. We know that the transform of G circle is G, and the transform of this complex exponential is just an impulse which is located at position L. Yes. Look, this is identical to G convolved with a Dirac impulse sitting at location L. Okay, so this again, this was a capital S was the shift operator, which is the circular matrix, which represents a convolution. So everything that you say is, or what I've understood is correct. So yes, this multiplication corresponds to convolution by a shifted impulse, which is just what the shift operator does. Okay, so you've done me the favor of mentioning the convolution theorem. So maybe one more application of this is when you want to transmit a radio signal. So let's say you have a speech signal, and this is its power spectral density. So let's say probably your radio moderator won't talk ultrasound. So Let's say the spectral density may look something like this. And here the normal tones are somewhere in the order of a kilohertz. But now you want to transmit this, let's say with ultra high frequency, you want to transmit this using megahertz, not kilohertz. So what you need to do is to shift this spectral density from the kilohertz range to the megahertz range. And you can accomplish this. So let's say this is 104.7 or whatever your favorite radio station is. And you now have the spectral density here. And you have it again at somewhere there. Now how to go from here to there? Yeah, shift in frequency. And how do you achieve it? Yeah, signal modulation. Yes. So you, in this case, if you want to have a real signal, you would multiply in the spatial domain. So this here was frequency domain. You multiply in the spatial domain with a cosine, which in the frequency domain gives you convolution with two impulses sitting, for example, at these frequencies. So in this so you convolve this with that to get the desired result. And we now have, well, this corresponds to a complex oscillation, that corresponds to a complex oscillation. Their imaginary parts happen to cancel. So in the spatial domain, this is the Fourier transform of a cosine. So you take your speech signal, you multiply it with a very high resolution cosine, and you get your desired result. Okay, but it's really already this famous convolution theorem that I'm talking about. The convolution theorem says that if I have the Fourier transform of A convolved with G, this is the same as taking the pointwise product. This is what I mean by the symbol, the element-wise or the pointwise product of the Fourier transform of A and the Fourier transform of G. Now the usual way to prove this is again by variable substitution and so on. No, you don't even need variable substitution. Okay, I will do both. I will do it the traditional way and the matrix way. So let's say that I call the result H. Then my transform at frequency K is and I'm now writing the operation of taking the Fourier transform. And I'm writing the operation of doing the convolution. So this is A convolved with G at frequency or at position J. Well, and the first part is taking the Fourier transform of that other thing. I can now reorder my summations. Taking the sum over L first. And then the sum over J. And now by virtue of the shift theorem, which we've just seen, I can rewrite this as a modulated version of the transform of A. So this is by the shift theorem, and note that we had a shift here. Okay, that gives me this is something that no longer depends on L, so I can pull it out, and what I get is that I need to multiply with the Fourier transform of my signal. So in other words, it's just what you saw up here. The convolution, the Fourier transform of the convolution is given by a dot-wise product of the Fourier transforms. I will now show you an argument that I prefer in terms of the matrix notation. So again, H is the desired output. And the Fourier transform of H we can write in terms of the adjoint of this matrix of Fourier coefficients. I insert this definition of H in terms of A times G. And when we'd studied this eigenvector problem, we had seen that AF equals F adjoint times this diagonal matrix, meaning that A is F adjoint the diagonal matrix no, there's some error here. That sounds more reasonable. And now I use this expression for A. This gives me F adjoint F. Which which taken together is n times the identity matrix. So this gives me square root of n times the diagonal matrix times the transform. Or if I want to write in terms of two vectors, then I would say this is the element-wise product of the vector with the A transform, so the Fourier transform of the impulse response, and the Fourier transform of the signal. Okay, I've really spelled this out in much detail, so I would say the arguing this in terms of matrix notation is faster than the above, element-wise. Okay, so thing to remember is that multiplication in space corresponds to convolution in reciprocal space and vice versa. Convolution in one domain corresponds to multiplication in the other domain. No, so that is correct to have this extra factor of square root of n here. Okay, and this makes for great computational savings, because if you implement convolution in the real domain, let's say convolution in space, is an order n squared operation, because we have two signals and we need to take this inner product of two signals of length n for each of the n positions, giving us n squared, whereas the pure multiplication is just O of n, but we have to pay the price of going to this other domain, which with the fast Fourier transform is n log n. So instead of a naive O(n) squared implementation of convolution, we can Fourier transform both signals, multiply them in reciprocal domain, and then inverse transform them at another cost of n log n to get the identical result. And you know, n log n is practically linear. N squared is too expensive for any sizable signal. So this is something that you really want to use in practice. So I will omit some of the properties, jump straight to the pictures, because I do want to make sure that we get to see them today. But before I show you pictures of 2D transform, I need to introduce it at least. Okay, so 3 or 4 more lines, 3, and then pictures at last. So the p-dimensional Fourier transform. We've talked about 1D signals all day long, but it's a lecture on image analysis, so it's appropriate that we go to higher dimensions. I introduce a couple of indices, J1 up to JP. I assume that my image is a hyperrectangle which can be indexed by J1 up to JP. And I collect all of these indices j1 to jp in one vector j, and I similarly have one vector k. And if my hyperrectangle of data is actually a hypercube, then I could simply have this division by n that we've always seen all day long. But if my data can have different sizes along different dimensions, then I need to use a diagonal matrix here that holds the spatial extent. And this is what I mean here by dimensions for each index. All right, and this thing, so what I have here is it's an exponential which sums over the dimensions. And an exponential of the sum is the same as a product of exponentials. So I can say this is a product of appropriately formed exponentials, and it's this form that I'm using now to reorder the summations. In particular, I'm starting first with the summation over just J1. J is again a full vector of indices. And this is multiplied by the second term. And I need a summation over the second index. And so on and so on. Sorry, this was jumping too far. This is JPKP. Okay, now note that this here is just a 1D discrete Fourier transform. So we have a hypercube of data, and we first transform along one dimension of this hypercube. And we then take another 1D discrete Fourier transform along an orthogonal dimension, and so on and so on. And this property is called separability. So the p-dimensional Fourier transform is separable. And that is a very favorable property because it means our cost is not going to explode with dimensions. It's simply number of dimensions times the cost of a normal discrete Fourier transform.